All right, so looking at these different phase changes, you were going to just say whether they were endothermic or exothermic. So the first one is freezing. Would that be an endothermic process or exothermic process? Exo. Got to get rid of some energy. What about evaporating? That would have to be endo, right? Because I'm going from a liquid to a gas, so I'd have to get some energy in. Melting, endo. And condensation would be exo. And the way that I think about it, although I've been getting mixed up this morning, I will say the opposite. But I think of it like what the particles are doing. So like if I'm freezing something, I'm going from a liquid with the particles are kind of moving medium down to where the particles are barely vibrating. So I got to get rid of some energy. So that's how I think about it. And they go together. Freezing and melting, that happens at the same temperature, and evaporation and condensation happens at the same temperature. So one of them is going to be an exothermic process, and one of them is going to be an endothermic process. All right. All right. All right, so we are right here on phase changes, which we've talked about before, but now we're just putting the energy portion of it too, along with it. So phase changes occur when a substance changes from one state to another, and it's a physical change. It's not a chemical change. And for a phase change to occur, there has to be some kind of change in energy. Either it has to be added or it has to be taken out. So if we talk about melting, for melt, I'm just going to put melt freeze, or evaporation, condensation. These happen at the same temperature. For water, this is here, this heating curve is water's heating curve. So melting and freezing both happen at 0 degrees Celsius. Evaporation and condensation both happen at 100 degrees Celsius. But one of them is a endothermic process and one of them is a exothermic process. So we said melting was endo, freezing was exo, and then on this side, my evaporation, that would have been an endo, and condensation would have been an exo. And that becomes important a little bit when we start talking about some numbers, where the same number is going to represent those processes, but one would have a positive sign and one would have a negative sign. So this heating curve, you can see here's my temperature. So it's increasing as I go up. This is the heat that's being added. So if I start off down here on this portion when the water is ice, if I add heat, it causes the temperature to go up some. So that means it's changing its kinetic energy. But when I'm flat right here, that's when the phase change is occurring, when the ice is being changed to water. So energy is still being put in, but there's no temperature change. Temperature changes, the temperature is the same. So that means the potential energy is being changed. Once that phase change is completely through, then I have another curve. And so I'm putting in some heat and it's causing, and this time I'm putting in a little bit of heat and it's causing a great big change in temperature. And then I get to my second flat portion, whereas my second phase change happens. That's when my liquid is going to a gas. And once again, a lot of energy is being put in, but it's causing no temperature change. And that's because it's changing the potential energy. And then when I get past here, then my water is water vapor or it's in a gas. And so then as I put in the energy, I will see a temperature change. So during a phase change, remember triangle means change, and that's the flat portion. the heat energy, and I just use a big E for energy because we're going to use it a lot here. The heat energy is added, but the temperature doesn't change. And that's because the potential energy changes. When we were doing especially gas laws, we talked about the kinetic energy can be measured by temperature. So if I don't see a temperature change, that means my kinetic energy isn't changing, but my potential energy is. During other portions, so portions where you see a little bit of a slope, or some depending on their specific heat, we'll see a greater slope. So during other portions, the heat energy increase does increase the temperature. So that means in those portions, the kinetic energy is changing. So what's happening during those flat portions when the potential energy is changing, it's all being used to break the intermolecular bonds. All right, are we good? When we get finished with them. All right, so reading a heating curve, the temperature rises quickly when the solid or the liquid or the gas phase is heated. We said that's because the kinetic energy is changing. The higher the specific heat of the substance, the shallower or less steep the line of the heating curve, and the stronger the intermolecular forces. So what that is all saying is that it takes more energy to cause a change. So water has a very high specific heat. So you can see that that took a lot of energy to cause those phase changes, especially that second phase change. The higher the enthalpy of the change, which is either going to be vaporization or fusion, depending on which phase change we're looking at, the longer the phase change time. And once again, that's very long for water, especially when it's going from a liquid to a gas. At a phase change, the temperature of the substance does not change because all of the added energy is used to break up the IMFs. And remember, IMF is intermolecular forces. So that would be the forces that are holding like the water molecules together in this case, or I don't know, we may phenol molecules together or butane molecules together, whatever we're looking at, but they're holding the molecules together. All of the energy change is potential, not kinetic, during phase changes. And the stronger the IMFs, the longer the phase change takes. So does anybody remember what kind of IMF water has? So you also learned about it in biology. Hydrogen bonding, which is the strongest IMF there is. So that's why it has such a specific heat, and that's why it takes so long or so much energy to cause a phase change, because it has the strongest type of intermolecular force. So if you're looking for an energy change without a phase change, so these are places not on the flat line, we just use our formula that we've used before. Q is equal to MC delta T. As far as your specific heats, different phases have different values. So we've been using with water the 4.18 for a liquid, but you'll see that those are a different value for steam, and there's a different value when it's an ice. Okay, so you just use the same thing that we've been doing if we're looking at our energy changes on those portions of the diagram. And we'll just do a quick example of that. So this is without the phase change. So how much heat is needed to raise 250 grams of water from 25 degrees Celsius to 100? So I'm just causing the water to increase in temperature. It doesn't say that I'm taking it through that phase change. So Q is going to be my mass, 250 grams. Specific heat is in the liquid phase, so that's still going to be my 4.18 joules per gram degree Celsius. And then my temperature would be my final minus my initial, which is going to give me 75 degrees Celsius. I would have 3 sig figs because of the temperature. Right here and right here was 3 sig figs. So Q would be equal to 78,400 joules is what I got. And it's a positive, and that makes sense because that is an endothermic process. Now, if we are at a phase change, the formula is actually a little bit easier. Because remember, if you're at a phase change, the temperature is not changing, so I wouldn't have a delta T if I'm talking about a phase change. So we're going to be using some other things besides specific heat. So the heat of vaporization is the heat that is required to vaporize 1 gram of a liquid. And we call this the heat of vaporization, or delta H of vaporization. So this is whenever it's going from a liquid to a gas, which would be an endothermic process. And then we have heat of fusion, which is going to be our other phase change, and that's the heat required to melt 1 gram of a solid. And we call that the heat of fusion, or delta H of fusion. So this is whenever I'm going from a solid to a liquid, which is also endothermic. So these two, heat of vaporization and heat of fusion, would be done on a heating curve because that's an endothermic process. So at a phase change, your formula is simply Q is equal to M times your delta T. I'm not your delta T, your delta H, and it would be either delta H of fusion or delta H of vaporization, depending on which phase change that you're doing. So the delta H of fusion for water, these are going to be water values, because those are kind of the most common ones that we do. The delta H of fusion is 334 joules per gram. And the delta H of vaporization is 2,260 joules per gram. So this one, delta H of vaporization was that second real long line, and it makes sense that it requires a lot more energy for that to have to happen. At the freezing point, melting point, you would use the same values, but different signs. So it's either called the heat of fusion, which we talked about, or if we're going back the other way, it's the heat of solidification. Still the same value. So in other words, the heat of fusion for water is 334 joules per gram. The heat of solidification for water is negative 330 joules per gram. The numbers don't change. You just have to tack on a negative side if instead of heating, you're cooling. And same thing for your boiling condensation. So freezing is an exothermic process. I keep getting myself confused today. Yes, I have to get rid of it. Thank you. Okay. I had to really think about that. So that would have a negative value. Melting is a endothermic process. That would have a positive value. So you would do your heat of fusion, the same number, but you would have to tack a negative sign on it if you were freezing something. Boiling is an endothermic process, so it would have a positive value. And condensation is an exothermic process, so you would have to have a negative value. So in other words, you may have to change the sign. And like I said earlier, remember there is no temperature change during a phase change, so that's why our formula ends up getting simplified a little bit. These values that I gave you for water are in joules per gram because they match up with the specific heats that we've been using. Sometimes you may see them in kilojoules per gram or calories per gram, but we're going to stick with the ones that match up with our specific heats. Trouble getting that out. All right, so let's look here what we got going on. It says how much heat is needed to change 250 grams of liquid water into steam at 100 degrees Celsius. So this is a phase change. The temperature stays at 100 degrees Celsius, so it's not part of my formula here. So Q is going to be equal to M, my mass. And then if I have a liquid going to water, that's heat of vaporization. And that value for water is 2,260 joules per gram. And so you simply multiply those two. We need 4 sig figs because just like with specific heat, things like heat of fusion, heat of vaporization, or that's not part of our sig figs. So you get, did I use the wrong number? Yeah, that's heat of vaporization. I wrote VAP. 2,000, yes, a larger number. So 565,000, but that's 3 sig figs. So the only way you could get this number into 4 sig figs is to put it in scientific notation. All right, so if you're freezing something or if you're melting something, or if you're evaporating or condensation, then that's going to be the formula that you use because there's no delta T. And I know some of you are like, I don't really care because I don't have to take the test. And I understand that. But you may appreciate it when you take chemistry sometimes and you have a little memory of it. Say, oh, Miss Lowry did mention that. So if I wanted to find the energy change for a heating curve, you have to do each one separately and then add it up. So for instance, it says, what is the heat needed to raise 250 grams of water from 25 degrees to 100 degrees? That's the first problem we did. And then make it boil. That's the second problem that we did. So to get my Q total, is going to be my Q1 plus my Q2 that I just calculated. So that's 784,000 joules. That's how much energy it took to take it from 25 to 100 degrees and then to cause it to do a phase change. Yeah, let's try. Oh, so what do I have? I have one too many zeros. True, correct? Let's try that again. All right. How about that? That look good? I think I actually did it correctly on my paper. And then to cause it to go through a phase change, that would be my other number. And I simply add them all up. And there's no places behind the decimal. And I should have caught that mistake because the way that I had it written, it was taking more energy to cause that little temperature change, and it should always take more energy to cause a phase change. So for instance, if I gave you a problem, for those of y'all that get to take the test next week, if I gave you a problem and I started some water, let's say at -10 degrees, and I got it all the way up to 125 degrees, you would have to do 5 problems and add them all up. you'd have to do the temperature increase from -10 to 0. Then you would have to do the phase change. Then you would have to do the next temperature increase, then the phase change, and the final temperature increase. And then you would add all 5 of those up. So these problems can get pretty long. Pretty long. All right, so let's finish by labeling this. Let's see if I can move mine up a little bit. Okay. So if we look here, any kind of heating process, that is an endothermic process, and we would use a positive heat of fusion and a positive heat of vaporization. If I turned around and I started cooling things down, that would be an exothermic process. And I would have to take my value given for me for delta H of fusion. Lift up my H part. That's what happens when you take too many days off. And negative delta H of vaporization. We'll give them a negative sign. So on part A of a heating curve, you're using Q is equal to MC delta T. On part B, that's my first phase change. So I'm using Q is equal to my mass times my delta heat fusion, because I'm assuming this is a heating curve. So what would I use on C? Which formula? On that C portion, is there a temperature change? A little one, right? So I'd have to use my Q is equal to MC delta T. Because my temperature changed from here, from about 5 to 15. Then on my flat portion, what do I need to use? Yeah, my other one, right? M times my delta heat of vaporization. And then finally, I finish it out, and this could go on for a long time. And that would be my Q is equal to my MC delta T. And like I said, your C values probably would be different. You would have one C value when it's ice, one C value when it's water, and one C value whenever it's gas or water vapor. All right, so that finishes up our notes. And let me stop this. So you will see some of this on your test, because your test is only over thermochemistry. So you have some practice. Tomorrow is just going to be a chance to work on whatever practice you feel like you need to in preparation for the test. My people that are exempt, y'all will still have to come here for the test, because I can't let y'all out to go to the, I cannot let y'all out to go, don't worry, I'll take it with you because I can't find my room. I can't let y'all out like you're officially exempt, because they have attendance down there.